Good afternoon, ladies and gentlemen. My name is Matthias Fahland. I'm department head for photovoltaic technology at Fraunhofer FEP. We had been a member of Fabulous, and with the role which is in my position, I also want to highlight a little bit more the activities in the photovoltaic technology which we had undergone in the Fabulous project. At the beginning, I want to express my gratitude that we as the FEP could take part in this project for the last 5 years. It is always a pleasure for me to participate in European projects, and the reason is not only to develop something, but also to meet people from different countries. And here in this picture, which I have taken out of the proposal actually, I have highlighted how these partners had been distributed. Unfortunately, we had the corona pandemic in between, so that we could not be everywhere, but nonetheless, it was great to meet everybody here. So this is, in this slide, a representation of the different activities and pillars and project phases in the Fabulous project. You see here that I have highlighted the whole-to-whole pillar, which was one of them. In the last talks over these 2 days, not too much highlighted, that's why I want to put the focus on that one in my talk. So why do we do whole-to-whole? What's the motivation? So there are some things which are quite easy to understand. Of course, I have a substrate which is flexible, which I can use later on. It is lightweight also. But one should not forget that it is possible to make flexible substrates extremely thin. If you handle in the household your stuff, you have foils in your hand which are much less than 0.1 millimeter in thickness, and they are mechanically stable. You can handle them, and in the same way you can also handle it in technical products. You can make things very slim and lightweight, and that's something which is exploited in various, especially electronic and handheld devices. It's also important that the handling is safety, so there's no shattering of such a material if you cannot break it, in contrast to flexible glass, which is also such a thin film substrate, which is not so easy to handle in contrast to that. Easy logistics, that's also an important point which is not obvious from the first glance. If you take out a roll from a machine, then this roll can contain hundreds or even thousands of square meters of coated material. You easily can put it into a box and send it around the world. That's not a big deal. If you would do the same area, you want to send this around the world, some 100 square meters on glass, then it's quite heavy, and it's not so easy. It's some volume. It's not so easy to transport. That's something which is important also for factories. There are more factories which serve quite large geographic areas in contrast to glass handling, for instance. And of course, that's what normally is connected to the understanding of flexible glass. You have a low cost, the potentially low cost production. So if you exactly know what you mean and your machine is exactly built up in the way as you like it, then you have a very smooth production. You can code it, you can emboss something without interruption, and you can feed in your roll at the beginning, and you take out the product at the end, and that's all running continuously without any breaks, which of course is very much benefit. You can very much benefit from that if you want to have really large area processing. And last but not least, as a scientist, I can tell you it's an extremely powerful tool for process development because you can do whatever you want. You can change parameters and establish your process, and at the end you have everything on your roll, and you can take as much samples as you like to which is a very effective way of developing. I like it very much. So in the Fabulous, there have been several partners dealing with wall-to-wall technology. Apart from us, we have also seen from UNEMO Research and Nanocom already contributions in these 2 days also. Maybe even I forgot somebody, so excuse me for that in case that this was happening. And with these partners, different technologies have been connected. We have nano-implant lithography process, which was done on several substrates, among this also on flexible ones. We have crafting, we have coatings, that's especially our part, plasma etching technology, and not to forget special ways of inspection and measurement, which are connected to the moving plastic film. So here are some impressions from machines which are in Fabulous. I want to highlight at the beginning this wall-to-wall nano-imprint line, which we quite shortly had already seen yesterday in the contributions for UNEMO Research. It is in their facility. You see that there's a web width of 300 millimeter, and yesterday we have heard that there was had been running quite large production quantities of this machine. So as I said, this is an advantage of wall-to-wall. You can make large areas. Even on institute level, you can achieve considerable amounts of coated material. Here you see some impressions, some details of the embossing drum, and here are some examples out of the use cases and pilot cases and research work which was done in Fabulous on this wall-to-wall nano-imprint pilot line. One of the use cases which had been made wall-to-wall in Fabulous was this Swarovski use case, which was already yesterday displayed from UNEMO. That was a good example of a combination of nano-implant lithography for making specialized surface structure for achieving optical effects, plus deposition, in that case of a reflecting layer, which again, in combination with microstructures, created this unique appearance, which you see here on the video and also in the exhibition, which is in the room next to us. Here again, a picture of that. Now I want to switch a little bit more in detail to things which we did at Fraunhofer FEP. So our institute is one out of the 70 Fraunhofer institutes which we have in Germany. That's the largest research organization which is dedicated to applied research, especially. So each institute has its specialty. We have some overlaps, but it is basically covering a really wide range of various technical applications. And our institute is located in the southeast of Germany, in Dresden. You see the facilities there, which are close to the center of the city, and we are, I would say, a medium-sized institute with about 200 people working in FEP. Altogether, Fraunhofer Society has almost 30,000 people at different locations within Germany, but also some of them are abroad. The specialty of Fraunhofer FEP is that we have a couple of core technologies, of course electron beam technology, that's in the name, but also large area plasma and sputter technologies and some construction capabilities for key components. And so these are the core technologies, and what we are trying is to go into as many applications as possible with these technologies. Also the machines which we have are quite versatile, so we are not focused on a special branch, but we basically want to support everybody and be a part of the supply chain. This was also our strategy here in fabulous. So we are not a specialist in micro-optics. We cannot simulate some beam pattern or whatever. What we can do is implement our machines in such a supply chain as was realized here in use on pilot cases. In combination with other partners who did micro-optics, and especially in combination with a final user of the products, which is really a specialist in the application and the specialities of this special field of business. So the main technology which we have brought into the project was the active sputter deposition, which we can use for making different types of inorganic coatings on top of surfaces. And what we can do here is the wide variety of materials which we can deposit is highlighted in this picture here of the periodic table of elements. So everything which is in blue was already in our code from the metal point of view, and with the speciality of the reactive sputtering, we can extend the amount of materials deposited still considerably. Normally sputtering is something where the target is a part of the electric circuit, so you are somehow dependent on the fact that the target material is electrically conductive. But with the special technology of the active sputtering, you can overcome this restriction, and you can make a lot of compounds, especially oxides and nitrides. And this is something which is quite important for optical coating and for also the expertise which we brought into Fabulous, because these oxides and nitrides are quite important for achieving optical effects. So a typical thing you see on the right side here is a way of making physical colors, meaning colors without having an absorption material inside the layer. So it's based on interference effects. For instance, we discussed with this Swarovski use case. We discussed also to make to keep the thing in color, so that would be easily possible with this approach. It was not the intention of Swarovski, that's why we declined this, but from the technology point of view, it would have been possible to make it shining blue or red or something like this. So this can be achieved with layer stacks as we have shown here on the right. And it's very important to get them combined with micro-optics, because these physical colors, they have the property of a color shift when you are tilting them. And that's not every time that what you want to have. And with micro-optics, you can mitigate this property so that you finally can tune between the exact color and also the color appearance in the final application. So these kind of coatings we can make in large scale machines. As I have said, we have very versatile machines which can do a lot of various coatings. This is a roll-to-roll sputter coater with 6 different deposition chambers. So what we normally do is that we implement a roll with a polymer film into such a machine. The roll goes through the machine. It passes 2 chilling drums, and around the circumference of this chilling drum there are deposition stations, and the chilling drum is preventing the polymers from overheating. So we have only around about 30 Kelvin temperature increase, and with this we can deposit our layers on most of the polymers, also on very common ones like PET or PE. And we can, the stations here in this machine are separated from each other, so we can mix reactive and non-reactive processes and can make such layer stacks as I have shown in the previous slide in one pass, and with quite different materials. So I want to focus now a little bit more on the inline monitoring. So we had a big work package in Fabulous which was dealing with metrology. There we have compared various measurement devices, but some of the devices are directly in our machines implemented, and they can be quite useful not only for the sputtered or PVD deposited layers, but also for the microstructures themselves. So I want to start with this inspection machine, which we inherited from past activity which we had in our institute. So there was for a couple of years the development of OLED devices, also in old machines. And for these OLED devices, it was extremely important to have a minimum number of defects on substrates, because every defect could be a dark spot in the final OLED, and then the material was not, or the final device was not what you intended to want. So that's why we had this inspection device, and now we tried to use this also for pattern substrates, for substrates which have a microstructure on top of this. So that's not so easy, because every microstructure is primarily for this device a defect. Nevertheless, we could adapt the software in such a way that the device was capable of distinguishing between regular defects and real defects in the structure. And this we could demonstrate quite well in this one, which is shown here. So what you see here in the middle of this field are optical signals on the entire film, really the entire area which was coated, or which was embossed also in this case. You have a crossweb position and a downweb position, so different units, as you see. One is millimeter, the other one is meter. And what you can see here is that you have an increase of detected defects in a very regular shape in the downward direction, and that's exactly where you have the touching point of the shim, which was embossing the structure into the film. So you see a very regular distance. The height of the defect is not always the same, but the pattern is very clear. So that's something which is simply due to the shim. And in the downward direction, you also have some peaks, and these peaks then really tell you something about irregularities which come from the coating process. In this case, was the slot die coating process. There was something not exactly adjusted with the deposition thickness at these points, and that was clearly detected by this device. And it was a very valuable and successful tool, which we could transfer from the defect recognition on a flat film to a defect recognition on a pattern film. So another thing which we also have made in the project, which was in parallel to Fabulous, is the so-called hyperspectral imaging. In the hyperspectral imaging, you detect also from an area, which is here the XY plane at the bottom, the entire spectrum of light. So you have really a recognition of the spectrum, and you can determine thickness or other optical quantities based on this, and you can have much more information than you have only with ordinary spectral measurement. So the anonymity was already shown. So what I wanted to highlight is also that FEP can cure those materials also with electron beam instead of UV, which can be advantageous in some cases. And I think my time is over if you are standing. Okay, good. Then I want to conclude with one slide concerning an application which I have shown you, which is a bird protection film. which has a different contrast in the UV compared to the visible light. So what we exploit is that birds see the UV and we do not. So that's why we could have put all the contrast in the UV. And that has also something to do with microstructuring, because it's not a stray light, it was modified in that way so that it allows to have a recognition under different light conditions. So with this, I skipped the last two slides, and I want to conclude with saying thank you for your